それでは時間となりましたので、セミナーを開始いたします。本日座長を務めますのは、九州大学アジア・オセアニア研究教育機構創発推進コーディネーターのキム・シューマッハ准教授です。シューマッハ先生、よろしくお願いいたします。
Thank you very much. So I welcome everyone today to the Brownback seminar. And we are very excited about today's presentation, which will be on solid sorption cycles for realizing carbon neutral energy society, which will be presented by Professor Saha, who was born in Bangladesh and is currently working as a professor and principal investigator at the International Institute for Carbon Neutral Energy Research of Kyushu University. And he's a professor at the Mechanical Engineering Department. He received his bachelor's and master's in science from Dhaka University in Bangladesh in 1987 and 1990. He was the first Bose Fellow at the University of Dhaka from January 1991 to December 1992, and he received his PhD in 1997 from the Tokyo University of Agriculture and Technology in Japan. His research interests include thermally powered absorption cooling, refrigeration and desalination systems, heat and mass transfer analysis, energy efficiency assessment, and energy policy. He has published more than 400 articles in peer-reviewed journals and is currently working on multiple government-sponsored and government-funded research projects. We're very excited to have you, Professor Saha, and we are looking forward to your presentation. And just as a final note, there will be a Q&A at the end of the presentation where you can ask Professor Saha questions, and those can be typed into the chat. So please, if you have questions, please do write them into the chat box, and we will take them up during the Q&A session at the end of the presentation. Thank you very much. Professor Saha, I will hand it over to you.
Thank you very much, Professor Kim, for the nice introduction. And now I'll share my screen. Can you see my slides?
Yes, we can.
Okay. So thank you, everybody, for attending this Brownback seminar. And it is my pleasure also to say about our research activities. And so today I'll talk about solid sorption cycles for realizing carbon neutral energy society. And the content will be background and motivation, research themes, and research approach and research network, assertion principles, because it belongs to assertion field. Then we are working on thermally powered assertion cooling system, performance of assertion, desalination, cooling. So the idea is we want to give less energy, input energy, and want to get multiple outputs. So here we want to get water production and also cooling energy. And then of course, research is always ongoing and always we have to make improvements. So we want to give some hint about the next generation cycles, and concluding remarks will be at the end. So the background of this study will be like this. Oh, I'm just getting my pointer options. So here you can see we have some biomasses, and then we have carbonizations at 500 or 600 degrees centigrade with the nitrogen environment. And if we do chemical activation, it is Q-AOS activation, and then we can get our activated carbon. This is one kind of adsorbent materials, and we will show about some data biomass precursor, especially mangrove and waste palm trunk. And there are some other materials. So the very new one is the MOF. We call it metal organic frameworks. It has some advantages. and zeolite and also another popular things. So then what we want to do here is we want to know the science about these porous materials and the refrigerant things. So how we can shape the pores, we can make the pore depth, pore height, and how it will, if it is very close to our molecular size of this refrigerant like ethanol, HCFO, or carbon dioxide or water, so then it will absorb more. So we want to first know our science thing, and then by knowing the science, we can have some technological development. So this consists of 4 components here. So we have to have one evaporator, one condenser, and then one pair of heat exchanger. So I'll introduce a little bit of this thing a bit more. And our idea also to use either solar collectors or to use industrial waste heat sources to drive these cycles. So why we need this cooling? So worldwide power consumption for air conditioning alone is forecast to surge 33-fold by 2100. It's less than 80 years from now, as developing world income rises. So very successful Prime Minister of Singapore was Lee Kuan Yew, of course he's passed. But then journalist asked him the question, what is the secret of Singapore's success? So he answered tolerance among the different ethnic groups. Of course, this is one of the major reasons. But then another question comes, anything else beside multicultural tolerance? So he answered straightforward, air conditioning. So according to him, the first thing I did upon becoming Prime Minister was to install air conditioners in buildings where the civil servants work. So he did this thing in 1970s. And then another part is, of course, nowadays it's very important to have the society carbon neutral. So I put some definition of this thing, carbon neutrality. Japan's target of no greenhouse gases emissions on a net basis by 2050. It brings it into line with the European Union. So European Union and Japan wants to make carbon neutral by 2050. Which set a target of being carbon neutrality by the former Prime Minister Suga. Chinese President also Xi Jinping in September 2020 pledged to make his country carbon neutral by 2060. So the developed countries like Japan, EU, they will make it in 2050, and China also pledged to make it in 2060, 10 years later. And this is a kind of main list of activities of our laboratory. Professor Kim also introduced a little bit, but today we'll talk more about our our heat pumps. Then we have several components here. But if you want to optimize our system, we have to optimize our components also. So then in our laboratory, we do also a component system simulation for heat pumps. And another thing is, in the case of materials, we have to have advanced material, functional materials. So what we can do here is we can improve the kinetics, performance, and stability of the materials. And there is another thing we are working on, fast algae cultivation, negative CO2 emission, and biofuel. So what we are trying to do is we want to capture the carbon dioxide from industry and then use this CO2 for algae cultivation. So CO2 is absorbed, it is negative emission happening here. And through this, we can have our algae cultivation, and it can be used as our superfood, or even nori we can produce. And also we can have fatty algae, and we can get the biofuel. Another thing is a soft engineering. We are also working on energy assessment and policy. So how energy poverty elevation can be done with policy implementation, something like that. So here we have 2 things. Usually people work separately, material science people is very developed field in the world, and thermal engineering people also. But we want to bridge these 2 gaps. So that's why simultaneously working on material science and also in thermal engineering. In case of material science, we are also synthesizing materials, checking their properties. And in case of system design, we are also working on better heat exchanger design, make our system more functional, and we want to use the best material in our system. So we are trying to make this two things so that we can have good heat pump applications and also potable water applications and also carbon neutrality also as well. So this is kind of my research network. So this is a kind of our global map here. So here, as you can see, worldwide, I am collaborating with more than 25 countries and more than 100 plus institutions in the world. So here in Japan, also collaborating with at least 12 institutions and also many collaborations with Asian countries and also some with the US and also EU countries also. So we want to exchange our knowledge around the world. And then these all are the name of the people who have at least 3 collaborative journal paper with me. So it is more than 80 people now, and many of them are from Japan and also from India, some of them China, many of them from Bangladesh, and so on and so forth. So what is absorption? Those who are new for this field, so this is a kind of process where molecules of one species adheres to the surface of another species, and it's 2 types. One is a physisorption. Due to the molecular interaction, van der Waals is weak interaction, so the heat of absorption is 20 to 50 kilojoule per mole. So silica gel water is one of the example. Also activated carbon ethanol also example of this thing. Another is the chemisorption. So due to chemical bonds, heat of absorption is almost 10 times more than physisorption. And naphthalene nickel hydrogen is kind of chemisorption. So here they make very strong bond, and the other is very weak bond. So as I mentioned earlier also, we have multi-scale nature of absorption. So we have to know the science first, and then we can make the technology here. So initially what we do in our case, we want to make some mathematical modeling with our things, and then we have some engineering system design, and then we can make some technological innovation. So to do these things, so first you have to know the force of the adsorbent materials, then how particles behaves in a component like heat exchanger, then make a functional or optimized heat exchanger, and combining several heat exchangers, we can make our absorption system. So to do this, so as I mentioned here, so you have to know the force, the particle, and then heat exchanger. It is like copper tube and aluminum fins, how this behaves, and then we can make our system functional. And there are many adsorbent materials commonly used. One is the zeolite, then silica gel, activated carbon. Initially, when I worked, so the systems are made of silica gel based, and then also these days we can work on metal organic frameworks and activated carbon and other things. So cooling system, how this work? So in the absorption cooling system, we need 4 heat exchangers. So the bottom part, this one is our evaporator, and the top part is our condenser here. And we have 1 pair of heat exchangers. They are identical in principle. So in this heat exchanger, this is in our system. Initially, we used silica gel water-based system. So we pack silica gel inside the fins, and we have used the net to pack the thing so that silica gel never drops out. And here you have our copper tube, so that heat transfer fluid can go through these tubes here. So in the system is the vacuum condition system. So the pressure is 1/100th of the atmospheric pressure, about 1 kilopascal. So in this pressure, water evaporates and it goes through valve 4 to our adsorber bed, and absorption is happening here. And due to the properties of exothermic properties of adsorbent materials, so heat generated in this bed, and we need to cool down the bed. On the other hand, here you can see the valve 2 is closed. So we are using, instead of cooling water here, we are using some hot water. This is our heat source. So we can take this heat source either from solar energy or from waste heat sources, about 80 degrees centigrade. And then we regenerate the water which is inside the heat exchanger. So one pair is in absorption mode, the other is in the resorption mode, and then vapor goes through valve 1 to the condenser. And also condenser is also water-cooled condenser. So we are cooling down this vapor, and then phase changes in this condenser, and the liquefied water again comes to the evaporator. The science here is when water evaporates, it creates some temperature difference. So for example, water inlet is about 12 degree and the outlet would be about 7 degree. So then the temperature difference can be used as the cooling energy. So if you have more water inlet flow rate, so you have more cooling energy. Of course, it depends on the size of the system. So we can work on this thing. So what happening here is after some minutes, like 7 minutes time, most of the water vapor and the silica gel bed, they are in saturated condition. Like if I have 10 kilograms of silica gel in this heat exchanger, so after 7 minutes, about 3 kilograms of moisture can be absorbed. So it is nearly saturated condition. So very difficult to absorb more. So in this sense, so we have to change the operation mode of this cycle. What we are doing here is we close all 4 valves here, and we are using, instead of cooling water, we use some hot water here. So we are preheating this cycle, and at the same time, we are using, instead of hot water, we are using cooling water here, and then we are pre-cooling this cycle. So this is, for example, so this bed will go for desorption mode in the next 7 minute time, and this will work as the absorption mode in the next time. So that's why we are call it preheating and pre-cooling mode for this cycle. And here you can see this is the opposite of the cycle A. Now this is our desorption bed, and moisture goes from this bed to condenser, and water vapor from evaporator goes to this our adsorber bed via valve 2. So this is opposite of our cycle A, and we can continuously get our cooling energy from this evaporator. So this is the way we are doing here. So then again we have to close all 4 valves and then pre-cool this one and preheat this heat exchanger so that it can go to the next level. So continuously it can work of heating, cooling well. So these are the cycle operations of this thing. So as I mentioned, 7 minutes it will be absorption mode or heat exchanger 1. Then 30 seconds we'll isolate this thing, and then also it is not connected with the valve 1, and then also not connected with the valves. But after that, 30 seconds, all valves are closed here. But then again, this 2 works in the mode with the valve 2 and simultaneously like this. So our heat exchanger is like this. Initially we give hot water for the desorption process, 7 minute time. Then it goes for the pre-cooling for 30-second time. Again goes for absorption for 7 minutes and preheating for 30 seconds. And other bed is completely opposite of bed 1. So here we are using cooling water and then hot water, and also cooling water. So these are the process it can work. So how our things work here? So for example, this is the little bit of technical part. We take diagram of the thing. So this is our like absorption happening in this case. So here we have the silica gel percentages about 17.5 to 2.5. So our preheating mode, our desorption, like moisture is going out from the bed from 17.5 to 2.5%. Then here we have the pre-cooling for 30 seconds. No concentration difference happening, but it's only cool down. And then our absorption is happening here, not temperature changing, but our amount of moisture increase in this cycle. So from here we can determine the heat source temperature. Of course, if we increase the heat source temperature, we can get bigger rectangle. That means we can get more cooling energy. And we developed many cycles. One is single stage cycle, then 2-stage cycle, and 3-stage cycles. Here the changes are like this. In single stage, we have 1 evaporator, 1 condenser, and 1 pair of heat exchanger, silica gel bed. But in 2 stages, of course, we have 2 pairs of heat exchangers. And in 3 stages, we have even more, 3 pairs of heat exchangers. So what is the benefit of doing all this thing? So the benefit is like this. So we also developed one dual mode cycle, combining single stage cycle and 3-stage cycle here. As you can see here, if you use solar energy, for example, as our heat source, so if it is a sunny day, of course, we'll use as a single stage cycle like this one, and we can get cooling capacity. If it is a 5 kilowatt capacity, we can get about 5 kilowatt after 80 degree heat source temperature. But if the temperature of heat source become below 60 degree, it is very difficult to run the single stage cycle, but 3-stage cycle can operate, and it can give you cooling capacity of 2 kilowatt capacity. And we make a dual mode cycle or combining these two cycles. So in any conditions it can operate it. If it is good sunny day, it will give you more cooling energy. If it is less, also it will give you cooling energy. But if it is only a single stage cycle, it cannot work in this temperature ranges. Same for the COP values also. With the COP for the single stage, we can get experimental values about 0.47, but with 3-stage mode, it is only 0.2. But here you can see our outside temperature is 30 degree, our heat source is 40, only 10 degree temperature difference, and we can get our cooling capacity and also COP values, which is very, very important and interesting as well. So we make many cycles, as I mentioned here, single stage cycle with the coolant temperature we kept experimentally 30 or 31 degrees centigrade. The operation ranges are for single stage is 65 to 95, and our COP varies from 0.31 to 0.62. This is the coefficient of performance. But if we want to make 2-stage cycle, we can use less heat source temperature, less low temperature, like about 60, but we have to sacrifice our COP. Then 3-stage cycle also developed. It can work with even 40 degree heat source temperature with a COP of 0.12 to 0.23 values. Then we have 4-bed regenerative cycles, which is about little bit of higher COP values we can get from this thing. And finally, I showed the performance of the dual mode cycles. So it can operate from 40 to 95 degree heat source temperature. And in the single stage mode, usually 80 degrees the rated condition. For 3-stage mode is 550. And then COP also varies from 0.12 to 0.62 values. And then desalination cycles we briefly introduce. So here we initially showed you we have one evaporator, one condenser, and one pair of heat exchanger here. But here you can see I used 2 heat evaporators here and 3 heat exchangers because we want to make the system more optimized. That's why we use 3 heat exchanger here. And as I mentioned here, water vapor goes in this bed, absorbed, then dissolved from this bed, and the moisture comes to the condenser. We use the cooling water to cool down the condensate, and it comes back to our evaporator so that we can get our cooling energy. But here, instead of getting our refrigerant cool down back to the evaporator, we are having this water. When it is cooled down, we store it in a potable water tank, and this is as good as distilled water, the water what we are getting, and we are charging our like water continuously, like seawater, in this evaporators. One is the high pressure evaporator and the other is the low pressure evaporator. So we can get many useful effects from this cycle. So here this temperature can be used for room cooling. This is we can use for process cooling application, and the water from the condenser we can get as our portable water. So this is very good, exciting results we got. Only one heat source temperature, we are getting 3 energies from the same cycle. And this is the experimental photograph of this cycle here. And then, of course, as I mentioned here, our low pressure evaporator is here, so we can get very high grade cooling. High pressure evaporator is there, and we have 3 identical heat exchangers here, and our condenser is here, and the 16 is our, of course, potable water tank, so that we can get cooling water as much as we want. Also, another thing is if we don't need any cooling energy of this thing, so we can use this energy to more cool down our bed, so we can optimize our water production also from the same cycle. It's depending on our situation. So how this works, it has a little bit of more. Instead of 4 modes, it has 6 modes. The bed one initially worked with the low pressure adsorber mode. Then also the switching period also, it is also low pressure one. Then it goes to high pressure mode with our things, and then it goes for the preheating, and then desorption, and also pre-cooling. Here we have some optimization is here, as you can see here. So initial 7 minutes it is as absorption mode, and also in 30 seconds also it also connected with the our adsorber or evaporator bed, and then it goes in the absorption mode and the 30-second preheating, and desorption mode is another 7 minutes. So our desorption mode is only 7 minutes, but the absorption mode is 7.5 minutes. It's more. So for having this optimization, we are doing these things, and the bed 2, bed 3 also doing the similar operations. So what kind of outlet we are getting? The average chill water outlet temperature from the low pressure evaporator is about 7.5 degree. So this one is our outlet temperature from the low pressure evaporator, and from the high pressure evaporator we are getting about 17.3 degree. So we can use this temperature like from 16 to 22 for the process cooling application, and this is very good for our room cooling applications. And these are the like temperature profile of our technical beds when it is in absorption. So then this is high pressure absorption is happening here, and when it is desorption, then increasing, and then temperature profile is like this. So this is the uptake profile of the bed 1, bed 2, and bed 3. So here you can see here the low pressure absorption absorber can absorb water vapor up to 0.13 kg per kg. That means if you have 1 kilogram of silica gel, it can absorb 130 grams of moisture, which the uptake by high pressure absorber is 0.232. It's much better than the low pressure one because of the temperature and the pressure of this thing. The pressurization effect by the introduction of high pressure evaporator significantly improves the uptake and provide additional cooling power. So we can get more cooling power from this high pressure absorber bed. So that is the novelty of this part. And then if we see the cooling capacity of this thing, so this is from our low pressure side, and this is from our high pressure side cooling capacity. The high grade cooling capacity, that is the outlet chill water temperature at 7.3 degrees centigrade, is found to be 7.1 kilowatt, which the cooling capacity at a relatively high temperature 17 or 17.3 degrees centigrade is about 10.8 kilowatt. The absorption cycle average water production, this is our specific daily water production, meter cube of water per day per ton of our silica gel is about 6.76 meter cube per day per ton of silica gel. So if we have 1 ton of silica gel system in our bed, the system will produce 6.76 tons of water in a day if it is continuously operating. Another thing I did not show here, if we don't need this cooling energies for room cooling or process cooling, we can use this cooling energy to cool down our beds so that our specific daily production can be improved from 6.76 meter cube to 12 meter cube per day. 12 tons of water we can get from this system. So this is a kind of single spool valve. So here in our systems, I just go quickly here. As you can see in the basic system, for example, we need at least 4 refrigerant valves here. 1, 2, 3, and 4. These are electromagnetic valves. This are expensive, and also it takes some sizes, but we can eliminate all these valves with our new innovations. Kind of single spool valve. This is a kind of valve here. So desorption bed, we have the high pressure things. So vapor pushes this spool. So this vapor through this channel can see the condenser. So like in the single stage cycle, and from the evaporator, our vapor goes through this channel, and through this channel it can see our absorber bed. So absorption happening in this bed, desorption happening in this bed, and dissolved vapor goes to the condenser. In the opposite cycle, when this bed becomes absorber, pressure is low in this bed and high pressure is in the left side bed. So this vapor pushes our spool so that vapor from this bed through this channel can see the condenser. On the other hand, vapor from the evaporator through this channel, it can go to the absorber bed. So we are getting continuously absorption, desorption processes, but we are using only one valve instead of 4 valves here. The valve is very promising. In this case, it is only 1 A4 size paper can be done. Another thing is we made some advanced hybrid heat exchanger. Usually people use only loose grains in the bed, but we are using some binding materials. We have some heat exchanger, which was we call it hybrid heat exchanging devices. Absorption are coated in the initial phase, and then we also have the loose grains here, so that we have more absorbent materials. So it improves the heat transfer performance and also more metals, so that we can get more efficiency. So it can increase the compactness of the heat exchanger, increase the thermal efficiency, and also the COP values of our heat exchanger. This is some of our patent to the industry. And then, as I mentioned about the spool bulb, this is the photograph of the spool bulb. It only have one A4 size paper. These are spool bulbs. So our whole system will be connected to this spool bulb, and then we can eliminate all these bulbs. And then to have better performance, we can use some composite material, and then we can make our system more functional and more compact. And with this note, I want to conclude my talk. So I can say that absorption is one of the most promising and sustainable technologies, and multi-stage absorption cooling cycle can be powered by low temperature heat source, 2 levels of chilled water temperature from 7 to 9 degrees centigrade and 17 to 23 degrees centigrade are produced for latent and sensible cooling. And concomitantly, it produces high-grade potable water of 6.5 meter cube of water per tons of silica gel per day, or you can improve it 12 meter cube of water if only water is produced in the same cycle. The performance of the low pressure evaporator, both in terms of specific cooling capacity and COP, is rather sensitive to the operating conditions. Absorption phenomena can be used not only for cooling but also for cooling cum desalination, which I already introduced. Also cooling cum refrigeration if you use alcohols, and other energy conversion applications, and thus helps in adopting 4 IER, even now 5 IER. And here I put 4 small symbols here. This is the HDG 6, which is clean water and sanitation, and then HDG 7, this is the for clean energy things, and then HDG 11, and also HDG 13, which is the climate actions. So we can contribute all these 4 SDGs. And with this note, I want to thank you all, and also I want to acknowledge our project with ISFAC. This is funded by Indian government, and this is a Mitsui Chemicals project funded by Mitsui Chemical Corporation. And thank you very much for your time and listening this talk.
Thank you very much, Professor Saha. This was very interesting, and I'm looking very much forward to some of the questions. And we already have some questions about, but first of all, I want to say or conclude that it's an extremely important topic because as one of the things that you mentioned is that the world will be in need of much more cooling in the future, and we need very innovative solutions to address that issue. And I think one of the takeaways from your presentation is that there are definitely innovative solutions. So looking forward to the discussion. So we already have 2 questions. The first one is, how about energy efficiency of adsorption chiller system? So for example, how does it perform in terms of energy demand versus, for example, comparable technologies that either desalination or cooling or like combined cycles? So how does it perform?
Thank you. So as I mentioned here, our objective is to use solar energy or waste heat sources. So this cycle will work as the bottoming cycle. For example, if you have a cogeneration cycle, you are using some micro turbines or whatever. So in this cycle, you are wasting the heat sources. So by tapping this heat, like 80-degree heat sources, we can run our cooling system. So that means in principle, our heat input is 0. We are not using almost any electricity, but of course we need very little bit of electricity to drive our pumps and fans. But this is very, very low. So the electrical efficiency of our cycle is extremely high. But of course, as the system is very big, so the initial cost is higher. But in case of energy, this is really very fantastic. So the energy you are wasting, so we will only tap that energy and use our cycle. We produce cooling energy or water production also using the waste heat sources. And as I mentioned here, it is not commercially available. The 2-stage or 3-stage cycle in Japan is even public bath. The waste, like the water temperature about 44 degrees centigrade. And even with this 44-degree heat source temperature water, we can drive our 3-stage cycle, and it can give you potentially cooling energy to cool down your room.
Thank you very much for your response. So I think that is very interesting. So like, yeah, theoretically, the energy input is reduced. So that should already like, yeah, be an advantage over existing systems. However, there's more questions. So one is by Professor Yokota, who says that please excuse my ignorance, but would you elaborate on how much CO2 and electricity, approximately minimum, will be saved in your new cooling system compared to current cooling systems? And can I just add to that? Because you mentioned one of the key components is access to clean energy.
Yes.
So I think that is one of the issues with electric vehicles. Unless the electricity system is not decarbonized, the actual decarbonization effect is not as significant. So for example, if the electricity system still relies on coal or on gas, natural gas, fossil fuels, ultimately it is not as efficient. So what beyond access to electricity or like the energy source, what are some of the advantages in terms of reducing? And you mentioned already some of those, but in terms of CO2, have you done any analysis? What could be the savings in its overall like, yeah, life cycle?
Yes, so in fact we did it, but I did not prepare this slide right now. Okay, I'll give you a little bit of example here. So in case of like normal cooling system, what we are using now, vapor compression system, it is really very user friendly. But still now we are using mostly we call it R134A, refrigerant 134A or 410A. These are the main refrigerants we are using in our vapor compression cycle. So if in every year there is some leakage from a system, this is the reality. About 5% leakage happening from any system. So when 1 kilogram of R134A, it was released to the atmosphere, which is happening, of course. So this is equivalent to 1,300 kilogram of carbon dioxide. We always say that CO2 emission is very high, very high. But if we have 1 kilogram of R134A release in the atmosphere, this equal to 1.3 tons of carbon dioxide equivalent. And in our case, the systems I showed you, this is using water as a refrigerant. So water has no emission, nothing. Of course, if we have some leakage, water vapor goes to the atmosphere. So in case of atmosphere degradation, nothing is happening. So we are really contributing to these things. And the desalination cycle also, there are some other things, the materials production and so on and so forth. Still, it is much better in case of CO2 emission compared to other competitive cycles.
Thank you very much. I think we have one, which is, we have one comment that is maybe not as relevant, but one of the viewers mentioned that congratulations on your achievements. What is the secret for writing so many good papers and a lot of citations? I think you can quickly answer it, but before that, I have a question that is more related to the topic. So I wanted to ask, in terms of life cycle, because obviously it is a process that requires certain amounts of chemicals, and so what is the environmental footprint of those chemicals? Are they easy to procure, or is it a very resource intensive process? And afterwards, in terms of disposing of or waste management of those chemicals, how does it actually work in terms of environmental footprint, overall environmental footprint versus existing solutions?
Well, thank you. So if we use silica gel, for example, in our system, what we are using now, So silica cell has no issue with the environment. We can dispose it as it is. And in fact, these days we are working on MOF materials and also activated carbons. So which is derived from, I did not show it in these things. So these activated carbons, it used for environmental pollutant recovery. So we can absorb VOCs, and even when there is some refrigerant system changes, then we can absorb this thing through our activated carbons. So it will, our things will always help the environment. So this is very sustainable from this viewpoint. Only our issues is the initial cost is because our systems is high, and also we are working on very high grade materials. So it has some more system oriented cost there. And then the question from the audience about my publications and these things. So one thing is, of course, we want to do things with the, if you have the new ideas and new topics, for example, like absorption cooling, it was a new topic when I was starting my PhD, in fact. Now we are also working on carbon neutrality with activated carbon capture. So this is something, so people want to follow this thing. This one. Another thing is, I must say, my co-researcher, like my postdocs, students, PhD students, so they are very active, and I am very lucky to get. So up to now, 37 people graduated from my lab as PhD student. I think most of them are very active, so we have more publications.
Thank you very much. And one last question. So to close it for today, there's one last question, and this will be the final question for today. Is there a limit of the absorption uptake for any adsorbent pair, and how can we assess it? So are there any limitations to scaling this?
So yes, there are some limitations. So depending on the materials, so some materials can absorb up to like 1 kilogram of activated carbon, the good one, it can absorb up to 2.2 kg of carbon dioxide. So this is the limitations here. So we cannot go beyond that thing. Another thing is, now we are a researcher, so we can say this is our synthesis procedure and this and that. But the scaling up should be done by real industries. Like for example, Mitsui Chemicals now funding us. So maybe at some point, if they are interested, they can scale it up. We can produce only grams of activated carbons, or maybe highly we can, in a month we can produce 1 kilogram. But when they want to make tons of this thing, they can make it really. So this is depending on the industry needs and their business model.
Thank you very much for this very comprehensive explanation. So with that, I would like to close today's session. And thank you once again, Professor Saha, for giving today's Brownback seminar presentation. It was very interesting. And the many questions show like, yeah, there's a keen interest into this topic, because especially people are very much aware that both cooling and desalination will become very important issues of the future. And any solution that tries to maybe even find two solutions at once are most urgently needed in our society. So your research is of high value, not only in a commercial space, but also just in terms of sustainability and humanity. So thank you very much again for presenting today. And we are looking forward to the discussion beyond that in this space. So thank you once again. And then with that, I will hand it over to the Brownback seminar team to talk about the next sessions. Thank you very much.
Thanks a lot. Thank you.
シャハ先生、シューマッハ先生、ありがとうございました。最後に事務局よりご案内させていただきます。まず次回のブラウンバックセミナーのご案内です。次回は来週9月13日水曜日12時10分より、システム情報科学研究院情報知能工学部門の井上浩二教授より、コンピューターを知ろう、動作原理から最先端研究までと題し講演を実施いたします。詳細はホームページをご覧ください。